Now let us rewind the case of benzene sulfonic acid being converted to phenol by fusion with the sodium hydroxide. Now before that, let us consider the canonical structures of benzene sulfonic acid. Now this pi bond will be polarizing or ionizing in this direction. We get S positive or negative. Now this pi bond will be shifting in this direction, so that positive charge of sulfur ionostates, and we get a positive charge here. This bond will migrate in this direction, creating positive charge here. This bond will be migrating in this direction, creating positive charge here. So we get these canonical structures. Now the speciality of these canonical structures is that the ortho and para positions are occupied by positive charges. The resonance hybrid will be having approximately this structure, and the delta positive charges are on ortho and para positions. Now a nucleophile like OH negative can attack these ortho and para positions. Now suppose a nucleophile attacks the ortho position in benzene sulfonic acid instead of this point. Now a negative charge comes in contact with this carbon. That means the lone pair of oxygen atom establishes a bond with this carbon. This carbon gains a negative charge. To neutralize the charge, this pi bond will be shifting in this direction. We get a negative charge here. Now this negative charge can form a pi bond here, simultaneous shift of this pi bond here, and simultaneous shift of this pi bond here, and the S double bond will be shifting, and so on. Now this is an intermediate. Now from this intermediate we have to reach the product, and there you take one of the intermediates, this one here. Now when this negative charge becomes a pi bond here, the benzenoid structure is retained. Then this structure becomes more stabilized. So the next step is formation of a pi bond between these two carbons by this negative charge. Then this carbon will attain a negative charge. So to neutralize the charge, either H negative or OH negative should be removed from this structure. Now carbon is more electronegative than hydrogen. The electronegativity of carbon is 2.5 and that of hydrogen is 2.1. So there is a very rare chance for removal of H as H negative because carbon is more electronegative. And again, H negative is not stable as a free ion. So the quality of a leaving group is that it should be stable as a free entity. Now here H negative cannot be formed for one reason: the carbon is more electronegative. So the removal of H as H negative is not easy. But OH negative can be removed easily because it is stable as a free entity. So what happens is that when this pair of electron denoted by this negative charge shifts in between these two carbons to form a bond, the OH is removed as OH negative and we get the sulfonic acid back. Now the same is the situation when the para point is attacked by OH negative. But when it attacks this carbon, the OH negative establishing a bond with this carbon, then this bond will be shifting in this direction and we get a structure like this. Negative charge here, bonds here, and SO3H and OH here. Now here we can say C2 bond is stronger and OH bond is weaker, and this negative charge becomes a bond pair, and this is SO3H negative is removed, so we get phenol. And This carbon called alpha carbon is made positive by the electron withdrawing character of the SO3's group. So there is a slight positive charge, delta positive, over this carbon, which favors the nucleophilic attack. And SO3H is a good leaving group. So we get S negative, double bond O, and OH. Now this can undergo resonance, giving S single bond O negative, and there the negative charge is neutralized because the share of electron of sulfur is given to oxygen. There is double bond O here and OH here. So you can say there is a pair of electron. Now when this electron pair moves in the direction in between S and O, that is a lone pair, we start from the negative sign to indicate that a lone pair is getting converted to a bond pair. Simultaneously this pair of electron moves in this direction and we get another canonical structure, a single bond O negative, lone pair here, double bond O and OH. So we say the HSO3 negative ion is stabilized by resonance, so it is more stable as a free entity, so it's a good leaving group. So that is why the OH negative nucleophile attacks the alpha position rather than the ortho and para positions. Now the acidity of nitrophenols. That's a question regarding the acidity of various nitrophenols. So we have three isomers, that is orthoisomer, orthonitrophenol, paranitrophenol and metanitrophenol. Now phenol is acidic. Why? Because the phenolate anion is stabilized by resonance. Now we can say the pK value of orthonitrophenol is 7.2, paranitrophenol is 7.1 and metanitrophenol is 8.3. So as pK value increases, acidity decreases. So that metanitrophenol is least acidic and paranitrophenol is most acidic, and orthonitrophenol is nearly acidic as paranitrophenol but slightly less acidic. Now all these acidic characters are based on the stabilities of the corresponding phenolate anions. Now consider orthonitrophenolate anion, this one. Now oxygen carries a negative charge. Now one of the lone pairs become a bond pair, and simultaneous shift of this pair of electron in this direction, this pi electron pair shifts in this direction, and this pi electron pair shifts in this direction, and this pi electron pair shifts over oxygen atom. So the initial shift started here, ends here. We say that is extended conjugation involving nitro group. Similarly, for paranitrophenolate anion, this pair of electrons will be shifting in this direction. The valency of this carbon is raised. To maintain the valency, this pi electron pair will be shifting in this direction. The valency of this carbon is raised. To maintain the valency of this carbon, this pi electron pair is shifted in this direction. Then valency of nitrogen becomes 5. To maintain the valency of nitrogen, this pi electron pair shifts over oxygen. In that sense, both these electrons are taken up by the orbital of oxygen, giving it a negative charge. So there also there is extended conjugation involving the nitro group. Whereas in the case of metanitrophenolate anion, the lone pair of O negative shifts in this direction. Then to maintain the valency of this carbon, this pi bond will be shifting in this direction. Then the valency of this carbon will be increased. To maintain its valency, this pi bond will be shifting in this direction. Then the valency of this carbon is raised. To decrease its valency, this pi electron pair can move only in this direction. This pi electron pair cannot move in this direction because the valency of carbon, this carbon will be again 5. so that this pi electron pair shifts in this direction, means this carbon takes up both the electrons in the pi bond and becomes a negative carbon, so that extended conjugation involving nitro group is absent in the case of metanitrophenolate anion. So that explains the higher acidity of higher pK value of metanitrophenol or a lower acidity of metanitrophenol, because there is no extended conjugation in the case of metanitrophenolate anion, whereas in the case of orthonitrophenolate and paranitrophenolate there is extended conjugation involving the nitro group. But in metanitrophenol, the nitro group alone can cause its minus M effect. That is, this pair of electron moving in this direction, this pair of electron moving in this direction, this pi one moving in this direction, and this pi one moving over oxygen atom. So there is minus M effect operating in the case of nitro group, but that is not in conjunction with the BOH group. So metanitrophenol is more acidic than phenol because the pK value of phenol is 10 and 8.3 is lower than 10, means metanitrophenol is more acidic than free phenol, and that is due to the minus M and minus A effect of nitro group. But in the case of ortho and paranitrophenol, this extended conjugation makes the canonical structures more stable, and the anion, phenolate anion, is made more stable. Now again, paranitrophenol is slightly more acidic than orthonitrophenol, and this is because nitro group itself can show a type of resonance like this. Then the net effect will be nitro group connected to oxygen atoms with delta negative charges on both oxygen and the pi electron, partial pi bond character here and partial pi bond character here. Now there will be a delta negative charge created here due to resonance, and another delta negative charge created here due to resonance, and this pi bond will be shared between both NO bonds. Now this angle here should be 120 degree because this carbon is sp2 hybridized. Then this negative oxygen and this negative oxygen, this oxygen will be partially negative due to resonance. So this partially negative oxygen and this partially negative oxygen, or this oxygen can come closer to this oxygen, so that there is repulsion between these negative charges, and so this nitro group will slightly turn out of plane with the benzene ring. So now the benzene ring and the nitro group are lying in the same plane on the paper, but this nitro group will slightly turn like this, so that the repulsion between the oxygen atoms is avoided. There will be a slight turning, and then the resonance involving nitro group will be very slightly decreased, so that the stability of orthonitrophenolate anion will be slightly less than the paranitrophenolate anion, and that explains why orthonitrophenolate phenol is having a pK of 7.2 and paranitrophenol having a lower pK value and a slightly higher acidity. Then coming to the various methyl phenols, orthocresol, paracresol and metacresol. Now phenol is having pK value of 10, orthocresol is having pK value of 10.2, paracresol is also having a value of 10.2, metacresol is having a value of 10.1, and so we can say metacresol is slightly higher in acidity than ortho and paracresols. Now in the case of cresol is methyl phenol, that is, there is a methyl group in the ring along with the OH group. Now in orthocresol, the methyl group and OH group are on adjacent carbon. Then the corresponding anion from orthocresol. See, the CH3 group can show hyperconjugation, the CH bond shifting like this. To maintain the valency of carbon, this bond will be shifting like this, and this bond will be shifting like this, and this bond will be shifting like this, so that this carbon is made negative. So we get two negative charges on adjacent atoms. That makes this particular canonical structure highly unstable. Similarly, in the case of para-methylphenol, that is paracresol, the negative carbon and negative oxygen can come closer. So negative carbon and negative oxygen come closer in paracresol also. So this will be the structure of such a canonical structure in the case of paracresol. So that negative charge is on the carbon adjacent to negative oxygen. So these two canonical structures make the anion less stable, corresponding to metacresol, where in metacresol the anion from metacresol, the CH bond will be shifting like this, this bond will be shifting like this, this bond will be shifting like this, and this bond cannot shift in this direction, but this bond can shift in this direction, giving a negative charge here. And here the negative charges are far apart than in the anion of orthocresol and paracresol. So the repulsion between these charges will be less in the case of metacresol. So this canonical structure is much more stable than this canonical structure. So that makes the anion stability of metacresol slightly higher than that of orthocresol and paracresol. But in all these cases, ortho, meta and paracresols, the hyperconjugation of the methyl group induces electron density into the ring. So electron density when induced into the ring, the oxygen atom of the OH bond of phenol gets electron density by hyperconjugation. So it will be having a higher electron density around it due to electron donation by hyperconjugation, so that it will show lesser tendency to take up the electron pair in the OH bonds. So electron donating group will decrease the acidity of phenol, so that all cresols are slightly more acidic than phenol itself. So phenol is more acidic than cresols. The only reason is the electron donation due to hyperconjugation by methyl group. And again, metacresol is more acidic than ortho and paracresols because of the contribution of this canonical structure having a slightly higher stability over these two canonical structures from the anion of ortho and paracresol. Now there is a question: arrange the following compounds in the increasing order of acidity. Propanol 2,4,6 trinitrophenol, 3-nitrophenol, 3,5-dinitrophenol, phenol, 4-methylphenol. And 4-methylphenol is paracresol. We know paracresol is less acidic than phenol due to hyperconjugation by the methyl group, and an alcohol is less acidic than phenol because the corresponding anion of alcohol obtained by removal of H as H positive is not stabilized by any electronic effects. And again, alcohol, in aliphatic alcohols, the alkyl group shows a plus effect which increases the electron density around the oxygen atom of the OH group, and so the oxygen will be having a lesser tendency to take up or absorb or withdraw the electron pair in the OH bonds, resulting in a lower acidity. So among these compounds, propan-1-mol will be the least acidic, and phenol will be the second one, and 4-methyl phenol. 4-methyl phenol will be less acidic than phenol, so 4-methyl phenol will be the second one, and phenol the third one. And when the number of nitro groups in phenol increases, the electron withdrawing character of the groups increases. So as the number of nitro groups increases, electron withdrawing nature of the group increases, and so as the number of nitro groups increases, acidity increases. So you can say 2,4,6 trinitrophenol is most acidic. Then second comes 3,5-dinitrophenol, and third comes 3-nitrophenol. Then phenol, then 4-methyl phenol, and finally propan-1-mol. So that is the order of increasing acidity. So propan-1-mol less acidic than para-methyl phenol, less acidic than phenol, less acidic than 3-nitrophenol, less acidic than 3,5-dinitrophenol, less acidic than 2,4,6 trinitrophenol. Now coming to the properties of phenol. Phenols are associated, as in the case of alcohols, due to hydrogen bonding. Now most of the phenols are either liquids or solids due to the high molecular weight of the benzene ring present. So due to high molecular weight and hydrogen bonding, they are either liquids or solids. Then coming to their chemical reactions, they undergo esterification with the carboxylic acids in the presence of strong acids. Now esters are formed. Phenol, as in the case of alcohol, reacts with the carboxylic acid RCOOH. Now the OH group of acid combines with the H of phenol, removal of a molecule of water, and we get C6H5OCOR, and this is an ester because there is the ester group. Now there is the preparation of aspirin, that is this acetyl salicylic acid, and salicylic acid is orthohydroxybenzoic acid. Now what is done is orthohydroxybenzoic acid or salicylic acid is dissolved in acetic anhydride, which is a liquid. Now acetic anhydride is obtained by reacting acetic acid with the phosphorus pentoxide. So that two molecules of acetic acid eliminate a molecule of water and form CH3COOCOCH3. So two molecules of acetic acid, CH3COOH, CH3COOH, remove HOH in presence of P2O5. We get CH3COOCOCH3, CH3COOCOCH3. Now H of phenolic group combines with the CH3COO part, so that we get CH3COOH, acetic acid, and this oxygen atom is connected to this C carbon, C double bond O and CH3. This is called acetyl group. OCOCH3 is called acetyl group, and this molecule is acetyl salicylic acid, and that is known as aspirin. It is an analgesic, anti-inflammatory drug and antipyretic drug. Now coming to electrophilic substitution reactions of phenol. Now the OH group shows plus M effect, and there is also a slight minus A effect. But plus M effect is of greater magnitude than minus I, and due to plus M effect, electron density is injected into the ring. Especially the electron density accumulates in ortho and para position. So in addition to the pi electrons of benzene ring, the lone pair electron of oxygen atom in phenol also donate their electron density to the ring, so that the electron density accumulates in ortho and para positions. Now increasing the electron density of the benzene ring or in the benzene ring is called activation. And an OH group activates the benzene ring by increasing its electron density, so that an electrophile can easily attack this benzene ring at the ortho and para positions, because electrophile is a species seeking electron density. So electrophilic reaction occurs at the ortho and para positions, and since there is activation of the ring, milder conditions are only needed to undergo electrophilic substitution reaction by phenol. So even dilute nitric acid can nitrate phenol. See, for nitration we use a mixture of concentrated nitric acid and concentrated sulfuric acid, and here in the case of phenol, due to activation of the ring by plus M effect, even dilute nitric acid can nitrate phenol. See, 2HNO3 giving H2O plus NO2 positive plus NO3 negative, and NO2 positive is the electrophile. It attacks the benzene nucleus, benzene ring at the ortho and para positions. One H atom here is replaced by NO2 group. We get orthonitrophenol, and at the para position get paranitrophenol. Now orthonitrophenol, in orthonitrophenol the OH group and the nitro group are mutually bonded by a hydrogen bond. The negative oxygen establishes a weak bond with the hydrogen atom of the OH group, and this acts as a single unit. And in paranitrophenol, the nitro group of one molecule forms a hydrogen bond with the OH group of another molecule, and this particular hydrogen bonding is called intermolecular hydrogen bonding, and this particular hydrogen bonding is called intramolecular hydrogen bonding. Now intramolecular hydrogen bonding separates the molecule as a single unit, and if we are having a mixture of these ortho and paranitроphenols, the paranitrophenol molecules are highly associated due to intermolecular hydrogen bonding, and when we pass steam through this mixture, those molecules which are acting as single units like orthonitrophenol will pass along with the steam in the vapor stage, and so we can separate the orthonitrophenol from paranitrophenol, and this process is called steam distillation. And when steam is passed through the mixture, steam carries away orthonitrophenol molecules, and when the vapors are cooled, we get separate layers of orthonitrophenol and water, and this combination can be separated using a device called a separating funnel. So we can separate orthonitrophenol and paranitrophenol by this manner. Now concentrated nitric acid converts phenol into 2,4,6-dinitrophenol, also known as picric acid. So concentrated nitric acid is a strong nitrating agent here. All the ortho and para positions are nitrated, and this is called picric acid, but the yield is poor. Now, to get a better yield of picric acid, phenol is first sulfonated using concentrated sulfuric acid. Now we get 2,4 sulfonic acid derivative of phenol, and when this 2,4 disulfonic acid derivative is treated with the concentrated nitric acid, the nitric acid molecule splits as OH NO2, and NO2 part combines with the ortho point here, and H2SO4 is removed. Here also this bond breaks. Nitric acid splits as OH NO2, and NO2 part connects this para position, and at the same time, due to activation by OH group of the phenolic structure, this ortho position is also acted upon by an electrophile, that is NO2 positive, and we get this trinitrophenol, that is picric acid. Now, the advantage of this method is that sulfonic acid group is a good leaving group, so it can be easily removed during nitration reaction with concentrated nitric acid. And again, this sulfonic acid group is less electron withdrawing than nitro group, less deactivating, because the sulfur atom is less electronegative than nitrogen. So when phenol is nitrated using nitric acid, the entering nitro group can deactivate the ring by the -M and -I effect, so that when one nitro group enters, deactivate the ring, so that retards or lowers the speed of nitration of the second position and the third position. So each nitro group retards the reaction, and the further nitration is made difficult, so that using concentrated nitric acid, nitration is not effective, and the yield obtained, the amount of product obtained will be lower. Whereas sulfonic acid, the deactivation is less, so that the activation of OH group is not decreased so much as in the case of nitration of pure phenol. So we say the sulfonic acid tube can be easily replaced during nitration, and then the trinitrophenol can be obtained in a better yield. Now, other reactions, that is bromination reaction. Phenol can be brominated in a less polar medium like chloroform or a carbon disulfide. We get the monobromo derivative, that is orthobromophenol and parabromophenol. See, the OH group activates the ring so that easy electrophilic substitution reaction occur. So if you are using a non-polar medium or less polar medium, then the active nature of the reaction is decreased, because in a less polar medium, ionization of Br into Br positive and Br negative is made difficult or made less. But when bromine is present in a polar medium like water, active electrophilic substitution occurs. That means all the ortho and para positions are occupied by bromine groups. Now here bromine dissociates into Br positive and Br negative, and Br positive is the electrophile. The Br positive attacks the ortho position, and the pi bond will be shifting in this direction between this carbon and bromine, and we get a positive charge here, so that this intermediate is formed. Now this intermediate can be stabilized by resonance this pi bond will be shifting in this direction and this pi bond will be shifting in this direction, so that the positive charge here is getting neutralized and the positive charge obtained here is again stabilized by or delocalized by the lone pair of oxygen atom here shifting in this direction. Now this intermediate can remove an H as H positive, but here there is one disparity. A CBr bond is less stronger than a CH bond, or a CH bond is stronger than a CBr bond. Again, it is found that the CH bond is getting broken, not the CBr bond is getting broken. Now why the stronger CH bond is getting broken during this change instead of the CBr bonds? Now one reason for this behavior is that the transition state leading to the breakage of CH bonds will be one in which there is partial bond between G and H. There is a partial bond formation here. There is full bond and so this will be an approximate picture of the transition state leading to the product. So there will be delta positive charge here and delta positive charge here. Now this transition state can be stabilized by the plus sum effect of bromine. So this lone pair of electron may be partially donated here. This pi bond may be partially shifted to this position, and here also partial bond shift occurs, and here also partial bond shift occurs. So that the transition state leading to breakage of CH bond is stabilized by bromine, and bromine CBr bond gets partial double bond character during this process. So that may be the reason why the stronger CH bond is broken during this reaction. During any electrophilic reaction of benzene, the CH bond is getting broken, and this may be the reason because the partially formed pi bond is stabilized by resonance due to plus sum effect of the attacking group, that is we are here. Now tribromophenol is a white precipitate, and bromine water is reddish brown in color due to presence of bromine, which is dark brown liquid. And when bromine reacts with the phenol, the color of water is changed to that of water that is colorless. So that brown water is decolorized by phenol, and we get a white precipitate of tribromophenol. That's enough. Thank you.